All right, hello AP Calculus. Today I want to look at some of the optimization problems from 4.7. Now we did the notes and we did several problems in class. What I'd like to do now is I would like to do a bunch of the even-numbered problems from the exercise set. I realize that these are pretty tough. So let's take a look at a couple of different problems. If you've got your textbooks, go ahead and pause the video and then go get your textbook and open it up to page 334. And we're going to start by looking at problem number 4. All right, so I'm going to go ahead and read the problem to you, and then we'll do it. We'll talk about it. So problem number 4 says, find a positive number such that the sum of the number and its reciprocal is as small as possible. All right, so find a positive number such that the sum of the number and its reciprocal is as small as possible. Let's let x equal the number. Now remember, it said positive, so x has to be greater than 0. I know I have that constraint there. Now the sum of the number and its reciprocal, I'm going to let that equal my function, would be x plus 1 over x. That's the function that we want to minimize. What's the minimum value here of x? All right, so we know that to find the minimums, we're going to have to do the derivative. So if I take the derivative, I'm switching up colors here. The derivative is going to be 1 plus, now remember, this is x to the negative 1. The derivative of that would be negative, that should be a negative x to the negative 2, or 1 minus 1 over x squared. Now with the derivative, we're going to set it equal to 0 and solve. So 0 equals 1 minus 1 over x squared. I want to solve. Let's see, what can I do? If I factor out a 1 over x squared, if I factor it, 1 over x squared, what would I get left? Well, that would have to be an x squared minus 1. Makes the factoring this a little bit easier. So, what would make that equal 0? Well, there's nothing there, right? You can't plug in 0 for x. No matter what you plug in for x, you're not going to get 0 there. Here, I get x could equal negative 1 or x could equal positive 1. But remember our constraint. We have to have a positive number here. So x is going to have to equal 1. So the critical number is going to be 1. And the first derivative there is going to be less than 0. So we know it's going to be an absolute minimum at x equals 1. So this one is extraneous. There's my solution. Well, what's the other number? The reciprocal would be 1 over 1, which would also be 1. And 1 plus 1 is 2. So that would be the actual smallest sum. But x equals 1 is the number. That's my number. The number is 1. All right. Let's do another sample problem. As I'm doing these, I'm looking at my notes over there on the side. So if I pause every now and then, I'm just looking at my notes. It would be the same as if I was walking around the classroom with my notes in my hand, the yellow sheets in my hand, doing problems on the board. So bear with me. All right, let's see. What should we do next? Let's take a look at problem number 10 on page 335. All right, go ahead and open up, take a look at it. I'm going to read it to you. This is a box with a square base and an open top. Must have a volume of 32,000 cubic centimeters. Find the dimension of the box that minimizes the amount of material that's going to be used. So it's a box with a square base. Let's draw a diagram here. A box with a square base. So here is my square base, and it's going to be an open top box. Very important though, this is a square base. Now I'm going to be dealing with two different things dealing with this. I'm going to be dealing with the surface area and the volume. It is a right rectangular pyramid, so I know the volume formula is length times width times height. And the surface area is going to be a little bit interesting because it would be just adding up all the sides but not the top. Now if it's a square base, that means that each side here has to be the same. If I call it B and B, little b and little b for the length of the base, and I don't know what the height is, I'll call that h for a moment here. And if I use this, then the total surface area would be the base, which would be b squared. LH, I should, you know what, let's write this in terms of the variables that we just decided. It would be b times h. That's just the generic formula that's underneath there, length times width times height. But we're saying it's b by h, so I want to use the same variables here. So the surface area will be the area of the base plus, now do you see that these four lateral sides are all going to be the same area? B times h, b times h, b times h, b times h, and there's four of them. All right, so what else do I know? Well, I know that the volume has to be 32,000 cubic centimeters. So I'm going to use the volume formula here, and I'm going to say 32,000 equals b squared h. B times b is b squared h. I'm going to solve this for h. H equals 32,000 over b squared. Why did I solve this for h? Because I'm going to substitute it in there. So now here comes the magic formula. This is what we're going to try to minimize here in a moment. B squared plus 4b times h, which is really 32,000 over b squared. And of course I can simplify this. Let's clean this up here a little bit before we set it equal to 0 and work with it. My surface area is going to be b squared plus, let's see, the b and the b is going to cancel. I'm going to have 1b on the bottom. And 4 times 32,000, let's see, 64, what's that, 128,000? So there it is. There's the formula for the surface area. Now I need to take the derivative of this. Surface area is a function of just the length of the base here. And I get, let's see, the derivative of b squared, is that 2b or not 2b? That's the question. And then, sorry, okay. And then this is the same thing as 128,000 times b to the negative 1, so it would be negative 128,000 over b squared. Now let's set that equal to 0 and solve. 0 equals 2b minus 128,000 over b squared. I'm going to do the same trick that I did in the last one. I'm going to factor out, I'm going to factor out a 2 over b squared. And what do I get left? Well, what would this be? 2 over b squared times what gives me b? B cubed minus, and let's see, the b squareds I pulled out, the 2 out of there, 64,000. Set them all equal to 0, and again, there's nothing there, is there? Set this equal to 0, b cubed minus 64,000 equals 0, b cubed equals 64,000. Take the cubed root of both sides, and I get b equals 4 times 4, 40. All right. So remember, the problem asks us to find the dimensions. So the dimensions of the base is a square base, so it's going to be 40 centimeters by 40 centimeters by. What's the height? I had a formula for the height, didn't I? What was the height? The height is 32,000 divided by b squared. I don't know if I can get that in my head. Here we go. Let's see. 32,000 divided by 40 squared by 20 centimeters in height. Now, what is the surface area? I don't know, but according to the derivative, and set the derivative equal to 0, these dimensions will give me the smallest surface area. And of course, if I multiply all these together, I will get the volume of that 32,000 that I want. All right, let's take a look at another one. How about, let's see, I want to do a point and a curve. So let's do number 16. This is a good one. I like this one. Find a point on the curve. So I've got the curve 6x plus y equals 9. A point on that curve that is the closest to the fixed point -3, 1. Now in class when we did this one, we graphed it. And then we picked all the points and everything like that. I don't think we need to graph it now. We're looking at distance, so we know we're going to be dealing with the distance formula. Before I do that, though, if I think about this, here I've got the point -3, 1. Here I've got the point x, comma, and what's the y value here? Well, if I solve this for y, the y is going to be 9 minus 6x. All right, now you know why this is important, because a little bit later, this is going to be my x1 and my y1, my x2 and my y2 that we're going to substitute into the distance formula. x1 minus x2 squared plus y1 minus y2 squared. And if I square both sides, I get the distance squared is x1 minus x2 squared plus y1 minus y2 squared. And I'm going to minimize this distance here in a moment. Well, so it doesn't matter if I've got distance or distance squared. No, not really. The minimum distance or the minimum is going to be the minimum distance squared. It's really the same thing. So don't get hung up on this when we take the derivative in a moment. The important part is, how do I get rid of all of these things here? So let's see. So I'm going to say that this is going to be equal to x minus -3 squared plus y, which is 9 minus 6x, minus 1 squared. All right, let's clean this up here a little bit. X plus 3 squared plus 9 minus 1 is 8 minus 6x squared. I know I'm going to have to take the derivative here in a moment. I could use power rule here, but I'm just going to FOIL it all out and make it into a nice, well-behaved polynomial. X plus 3 times x plus 3 is going to be x squared. 3x and 3x is 6x plus 9, plus 8 times 8 is 64. 8 times -6 is 48, and another -48 is -96x plus 6 times 6, 36x squared. So here we go. We've got our nice formula now. 37x squared, 6x minus 96x minus 90x, and 64 plus 9 plus 73. There it is. So now we want to minimize this. We're going to take the derivative. And I get 74x minus 90. Set the derivative equal to 0. 74x minus 90. Add 90 to both sides. Divide by 74. 90 over 74. So there's, now what is that? What does that represent? Well, that represents the x value that's on this curve that is closest to that point. I can simplify that too, can't I? 2 goes into both of those. What's that? 45 over half of 74 is 37. So there we go. There's my x value. So that's the x value on that curve that's closest to that point. What's the corresponding y value? All right, so let's see. We need to find the y value. How am I going to find the y value? Well, as you can imagine, I'm just going to plug it into here. To find the y value, it's going to be 9 minus 6 times 45 over 37. Using the calculator, 9 minus 6 times 45 divided by 37 some horrible fraction, go math, convert it into, or some horrible decimal, convert it to a fraction, and I get 63/37. So, what is the point on this curve closest to that fixed point? It would be the point 45/37, 63/37. There's my answer. All right, let's do another one, similar to one we did in class as well. This is one that some people were asking questions about. You're seeing them in the homework. Let's do problem number 22. All right, so go ahead and find it, and I will read it to you, and then we'll work on it here. So let's see. Number 22. Find the dimensions of a rectangle of the largest area that has its base at the x-axis and the other two vertices above the x-axis lying on the parabola y equals 8 minus x squared. Y equals 8 minus x squared. We should know what that one looks like. We should know that the y-intercept is 8 and it opens down and it's not got any stretching. If I draw a quick diagram here of this thing, let's just draw a diagram. I know that the vertex is going to be here at 8. It's going to open down. Oh, I should have used a different color other than black. Oh well. And I'm interested in the inscribed rectangle that has the x-axis as a base and vertices, the other vertices, on the curve. And remember, this curve is the curve y equals 8 minus x squared. So I want to find those points right there. And I want to find the area of the rectangle that's going to be the largest possible rectangle. Well, I know that a rectangle has an area of length times width. That's my general formula for a rectangle. Well, what's the length and the width here? Well, if I think about it as the base, this value is x, this value is y. So does that mean it's x by y? No, because this is x as well, right? So it's really 2x times y. So the area is going to be 2x times y. X plus x is 2x's. Well, again, I can't have the y here. I want to write the area as a function of just x. 2x times, what can I substitute in here for y? Well, I know the coordinates of any y value on the curve. Any point has x and y, an x value, and the y value is this. So that's what I'm going to substitute in. I'm going to substitute in the 8 minus the x squared. Now we know we're going to have to take the derivative here in a moment, so let's go ahead and clean this thing up. I could do product rule, but it seems pretty simple here. 2x times 8 is 16x minus 2x cubed. Take the derivative, and I get 16 minus 6x squared. Set the derivative equal to 0. Subtract 16, divide by negative 6. 16 over 6 is 8/3 equals x squared. Take the square root of both sides, and the square root of 8/3 is x. And of course, that's not very good form, is it? If I wanted to clean that up here a little bit, I think I would write it as, let's see, what's that? 2 root 2 over 3 multiplied by root 3 over root 3. So, oh gosh, let me see. 2 root 2 over root 3 multiplied by root 3 over root 3, and I get 2 root 6 over 3. I think that's a cleaner, nicer, or we'll see. So I know the x-coordinate of the point on there. It asks me to find the dimensions. So if that's the x-coordinate here, I know 2 times that will be the whole. Whoops, I'm off the graph. I know the x value, so 2 times that will be the whole length. But how high is it? Well, it's the y value. Well, what is y? Y is 8 minus x squared. So now let's find the corresponding y. And I'm going to substitute in y is equal to 8 minus the x value squared. You know what? I'm going to use that. The square root of 8 over 3 squared. I'm allowed to use that because it's going to be a little bit nicer. So now I'm going to have 8 minus, that squared is just going to be 8 divided by 3. I'm going to convert that into a nice well-behaved fraction, and my y value is 16 thirds. All right, so now it doesn't say find the coordinates of the point. It says find the dimensions. So the dimensions, here comes the answer, the dimensions are going to be 2 times that, because remember, that's the x value right here. It's going to be double that. So if I do 2 times that, would be 4 root 6 over 3 by 16 thirds. That would be the actual dimensions of the largest rectangle that can be inscribed under that curve using the x-axis. All right, let's do another one. Let's see. I want to do one with a cone. Something inscribed. Let's do a solid. That cone one, I like the cone one. Let's do number 26. Again, similar to one we did in class. Hopefully you remember the trick for this one in class. It's going to be a cylinder inscribed in a cone. So let's take a look at number 26. It says, a right circular cylinder is inscribed in a cone with a height of h and a radius of r. Find the largest possible volume of such a cylinder. All right, so let's draw a diagram of what's going on here. First, here is my cone. And what do I know about this cone? I know the height of the cone. It didn't actually give me numbers, does it? This is going to be all done with variables. So it's telling me that the height of the cone is h, and the radius of the cone is r. Right? It just says the radius is r. But I have an inscribed cylinder inside of the cone. So here's my cylinder. And what do I know about the cylinder? Well, I want to find the largest possible volume of the cylinder. All right, so I need to start assigning variables here. Now, h and r, they look like they're variables, but I want you to treat them like they're constants. It's got a height of h, some number h, and the radius of the cone is r. I'm going to call the radius of the cylinder x. And if I call this height up here, I'm going to call this y, then the height of the cylinder would be h minus y. Take the whole height of the cone and subtract the bit that's up here, and I would get just the cylinder. Now, why am I doing all of this? Do you see? Oh gosh, the diagram's getting pretty messy here. But do you see the two similar triangles? I've got the triangle here, and I've got the triangle here, and the little triangle y and x, the big triangle h and r. Right? Do we see the two similar triangles here? Again, I'm going to think of h and r as numbers. They're fixed numbers. They're not variables. The x and y are the variables that I'm trying to solve for. Well, two similar triangles, and I know they're similar because these angles would be the same by angle similarity postulate. I know the triangles are similar, which means that y is to h as x is to r. So for y equals h over r x. And again, h and r are fixed numbers. So think about this as a number, as a constant. Okay. Now, what about the volume of the cylinder? Well, for a cylinder, the volume is going to be, let's see, what is it? It's the area of the base, which is a circle, pi r squared, times the height. All right, substituting in for my specific cylinder in here, I'm going to get that the volume is pi times, what's the radius? X squared times the height. What's the height? H minus y. Now the h is not a problem because the h is just a fixed number. The y is the problem. So I'm going to substitute from here, and I'm going to get that the volume of my cylinder is pi x squared times h minus h over r x. Now remember, h and r are just numbers. They're constants. Okay? I know I'm going to have to take the derivative and set this equal to a 0. So let me simplify things here. If I distribute, I'm going to get pi h x squared, and then multiply here, minus h pi over r x cubed. And again, remember, h and r are constants. So now if I take the derivative, I'm going to have 2 pi h x minus 3 h pi over r x squared. Set that equal to 0. 0 equals 2 pi hx minus 3 h pi over r x squared. And solve. It looks to me like I can factor out, what can I factor out here? Not a constant. I can factor out an h and a pi if I wanted to, or just, you know what, I'm just going to make it simple. I'm going to factor out just an x for a moment. I know it's going to make it a little bit sloppy. So let's see. 0 equals x times 2 pi h minus 3 h pi over r times x. So x could equal 0, or I need to solve this side here. 2 pi h minus 3 pi h over r x equals 0. Let's see, add that over, and I'm going to get, what am I going to get here? 2 pi h equals 3 pi h over r times x. Divide both sides by pi, the pi's will go away. Divide both sides by h, the h's will go away. Divide both sides by 3, multiply both sides by r, and I get x equals 2/3 r. Okay, so what does that mean? What does that mean? So what this means is that go back to the original diagram for a moment and look at this. That means that if I have a cylinder inscribed in a cone, the cylinder will have the largest possible volume if the radius of the cylinder, which is x, is 2/3 of the radius of the cone. All right, so what would be the volume then? So the volume of a cylinder, again going back to cylinder, volume equals pi r squared h. Volume equals pi times the radius squared times the height. The radius would be 2/3 of r. So if I simplify this, the volume is going to be 2 squared is 4/9 pi r h. Yeah, I think there we go. I think that's going to be what we want. I think that's going to give me my answer there. Am I missing something? All right. Let's take a look at another one. This was I'm going to pick another one similar to one that I know some people had some questions on, an awkward one in class, number 30. So go ahead and look at number 30. It says a poster is to have an area of 180 square inches with a 1-inch margins at the bottom and the sides and a 2-inch margin at the top. What dimensions will give the largest printed area? So here's my poster. And I'm going to have margins around it of 1 inch on each side and the bottom, and 2 inches on the top. Now, if I say the whole poster is x times y, the area is xy, and it tells me that the area needs to be 180. So for y, I'm going to get 180 over x. So what's the printed material going to be? Well, let's see. If this whole length is x, minus 1 minus 2, this would be x minus 2, and y minus 1 and 2 is 3. So the printed material area is going to equal length times width. The area is going to equal x minus 2 times y minus 3. But again, I want to get rid of the y. I'm going to substitute it in here. So the area as a function of just x is going to be x minus 2 times y, which is 180 minus x, minus 3. Now, I know I'm going to have to take the derivative of this in a minute, set it equal to 0. So let's clean this up. If I FOIL it out here, my area is going to be x times 180 over x is 180 minus 3x minus 360 over x plus 6. So my area as a function of x is going to be 186 minus 3x minus 360 over x. Let's take the derivative. And I'm going to get negative 3. Let's see, this is x to the negative 1, so negative 1 times that, plus 360 over x squared. Set it equal to 0. 0 equals negative 3 plus 360 over x squared. Add 3 to both sides. 3 equals 360 over x squared multiplied by x squared. 3x squared equals 360. Divide by 3, x squared equals 120. Take the square root of 120. Let's see, 120 is 4 times 30, so 2 root 30. So it wants me to find the dimensions of the printed material. So the dimensions are going to of the poster, the x and the y. Well, I just found the x. So the dimensions are going to be 2 root 30 by, oh, I don't know the y value. I need to find the y value. How do I find the y value? I need to plug this in here. So let's see. Let's find the y value. 180 over x, which is the square root, or 2 root 30 equals y. So 90 over root 30 equals y. Multiplied by root 30 over root 30. 90 root 30 over 30 equals y. What is that? 3 root 30. This is what I would say. Somebody check that on the calculator. 3 root 30. Oh gosh, if I make mistakes in here, I don't have you guys telling me all about my mistakes that I'm making. That could be frustrating. Well, if you spot a mistake, let me know. Put it in the posts or let me know. All right, guys, so that was just some quick examples that I wanted to do. I'm going to upload Next, I'm going to upload the notes from 4.8. A couple of people missed that on the Friday, so I'm going to put the notes in there. You might already have that. And then I'm going to do a bunch of even-numbered problems out of 4.8. All right, guys, good luck, and I'll talk to you again soon. Oh, wait a minute. I totally forgot about the assignment. All right, so what do I want you to do now? All right, so the assignment. Do 4.7 homework assignment. Now, I put the assignment list for Chapter 4. You should have it already, but I put a copy of it in the Teams files. So that's the same place this video is going to go. So look at it and access it from there, and go ahead and do 4.7. Some of you have already done it, but if you haven't done it, well, make sure you go ahead and do that. All right, guys, good luck. Talk to you again soon.